So, chapter 8 was kind of nice. We introduced the idea of negatives and positives. How did we represent those with manipulatives? What did we do last night? Yeah, exactly. So, like, red would be negative. We had to use blue. It's supposed to be black, but we had to use blue for positive, if I remember correctly. Normally, it's related to, like, being in the red. If you're a business and you're in the red, it means you're in debt. The couple things that I didn't quite cover yet, one of them was something I think we covered before, which was the book finally catches up to us, but just to make sure you guys remember, what's a negative power mean? So like if I have 2 to the negative 3, what's a negative power mean? I'm pretty sure I introduced this way back when we talked about exponents. The book didn't talk about it then because they weren't admitting that negative numbers existed. Do you guys remember what a negative power means? Sort of. Yes?
Do you put 1 over?
Yeah, so the reason I say sort of for fraction is it doesn't make everything a fraction, it just makes everything flip. So this would become a fraction, yeah, because those 3 2's would go down. I like it. And what happens? So for example, so that would be 1/8, right? Woohoo! All right, you are poor little dying marker. What happens if I do 2 to the 7th divided by 2 cubed? What do I get? 2 to the 4th, exactly, right? You have 7 2's, you divide 3 of them away. Of course, now you got 4 left multiplying, all right? Ooh, okay. What happens if I do 2 to the 7th times 2 to the negative 3? What do I do with powers when I multiply like bases? What do I do with the powers when I multiply like bases? Add them. So what's 7 plus negative 3? 4. So don't I get the same answer? Either way I do it, don't I lose 3 2's? Lose 3 2's? That's another reason why that's true. That's why a negative power is flipping, because a negative power is making you lose a certain number of things you're multiplying by, so that must mean the same thing as division. You guys get that? The first time I showed you this, I proved it a different way. I said, all right, if I have x to the 3rd up here, what do I need down here to make the answer x to the negative 3, for example? What do you do with powers when you divide like bases? Subtract them. What would have to be down here, x to the what, so that I end up with a negative 3 power? 6. And isn't x cubed x, and isn't x 6 x, right? This is all very exciting. So then I have 3 x's cancel, and I'm left with 1 over x cubed. So therefore, these must mean the same thing because they both come from the same place. Kick ass. So there's a couple different ways. I like this way, even though it's not a proof, because it's more of a feeling it out. They both do the same thing, so they must be equal to each other. This is more of a little more of a proof, because this is general. It doesn't have to be a specific x. I could even make the powers arbitrary. Okay, maybe. And again, I covered that a while back, but you just didn't get practice with it. Now in section 8.2, you're going to see some negative exponent problems. Okay, I like it. They come back. They also talk about scientific notation, because the first time we talked about scientific notation, they didn't have negative powers, if I remember correctly. Or did they? I can't remember now. Whoa, what's that? Yeah. So somebody help me out. Can you remind me what this would be in scientific notation?
4.1 times 10 to the 4th.
Careful.
Negative.
Yeah. And why does it make sense? Negative power means flip, so that times 10 to negative 4 is actually dividing by 4 tenths. Every time I divide by a 10, I get smaller. The decimal moves back, so if I divide by 4 tenths, it's going to move back 4 times. So this number is the same as that number. Feel like it? Okay, so scientific notation is actually a problem that works back out to be the number. That's all it is. Right? If you do that problem, you get that. What was the other thing? Was there another thing? I think that might have been it. Yeah, the last thing we talked about was how to order these things. The very last thing we talked about was reminding you what had to happen in a problem like this and why it happens. So if here I'm going to divide by -1, and of course what has to happen?
Sign flip.
Yeah. Can somebody tell me why the sign flips? There's a few different ways you can say it really succinctly. What does multiplying by a negative number do visually? What does multiplying by a negative number? So if I have 1 times -1, what's it do?
So makes it like opposite.
Yeah, it rotates it, right? So if let me put it over here. So if I have 1 times -1, it rotates it. So here, if I multiply by -1, I switch the side of 0 things are on. So therefore, the relationship between them shifts. Okay. So that's, I think, yeah, that's pretty much it. There were just a couple things I think I didn't cover, but we sort of covered most of them before. We just did it before the book got to negative numbers exist. Yeah, good. And then, okay, a couple things I want to say about chapter 9. Just remind everybody, I made chapter 9 homework, extra credit, because this semester I'm seeing what being nice feels like. Feels icky, but square roots, or let me say it more radicals. Oh shit. What does that, basically just gave it away, but what does the word radical relate to? Holy shit, that's a type of radical. So radical is the sign, and it could be a cube root 4 through, those are all radicals. Okay, so real quick, can somebody tell me what the square root of 25 is? Holy shit, why? Yeah, because 5 times 5 is 25. What's the understood number that's here? And there's a 2 understood to be there. We don't write it because the square root's the most often used root. So to save time, we just go, everybody knows it's a 2. Right? Let me freak some of you guys out. Does anyone remember, or does anyone ever work with something called a log? Go with me for just a second, all right? You know, like, that's all we ever freaking do, Jeff. Has anyone never seen logarithms before? Do you think? Okay. Don't worry. You're not going to have to know this. I just want to... Now, real quick. Why is this an easy problem? Right? Here's another one. What's this? Holy shit. The reason it's easy is because you know what sentence this symbol is replacing. That's all that is shorthand. Almost all in mathematics is shorthand. What is this asking you? Can you put that into words? What the question that this is asking you? What is that question? Why is the answer 4? What's the question asking you?
What number squared is 16?
Yeah, what number squared is 16? Or what does it take 2 up to multiply by 16, right? They all relate to the same idea. You've internalized what this means. So it is, math is a foreign language, as I tell people. It's just learning what the symbols mean. It's translation. This question is, what power does 2 need to become 8? Or asked in a different way, how many 2's multiply to be 8? Because that's what that power means, right? Well, how many 2's multiply to be 8? 3. 2 times 2 is 4, times 2 is 8. Right? Again, you're not responsible for understanding the logarithms for this class, but I just want to do this. So what would this be? Log base 3 of 9. What do you ask yourself?
How many 3's?
How many 3's does it take to multiply to 9? 2. So if I saw this, what's missing? The number that would be here, right? That number's missing, but we understand it to be 10. So this really says, how many 10s does it take to multiply by 100? 2. So the point is, the reason we don't write a 10 is because that's the most commonly used logarithm. We live in California. Ooh, I learned something today, Jeff. What happens in California sometimes that didn't happen to Jeff when I lived in Florida and Virginia? What happens in California sometimes? Earthquakes. How do we measure earthquake strength? Do you guys know? Really carefully. Richter scale, right? The Richter scale is actually a logarithmic scale. It's based on base 10. It's based on this being a 10. Why do you think 10 is the one that we don't do? Because our number system's based on 10. So that's kind of like, we call it the common log. It's relative to our number system. So square root, this is a 2. We never write the 2 because we just know it's a 2 because it's the most commonly used radical. Log, we don't put the 10. It's the most commonly used logarithm. You ever heard of decibels? Very often they talk about like a rock concert versus a freaking jackhammer, right? The decibels, the amount of sound. It also uses base 10 logarithm for that. Okay. So let me ask your opinion on this then. I don't like it. No, stop. What's the cube root of 27? Yeah. So now what's the question? This was the question, and what does it take 2 of, or what squared is 25? That would be what does it take 3 of to multiply 27, or what cubed is 27? So 3. I like it. So the most common mistake I get is the student's going to tell me that this is 9. What are they thinking? Yeah, 3 9s add to be 27, right? But what operation would I use to get 9 as an answer, not cube root? Cube root's based on multiplication, right? 9 times 9 times 9 is way bigger than 27. So they're thinking this. That means how many 9s add to be 27, right? Okay, maybe. You guys all with me? Again, this is all in the extra credit section, but I still wanted to throw this at you. Okay. Okay. I think that's everything I wanted to throw at you for right now. So what just happened was that was the last new thing for the semester. So just make sure everybody's on board. Let me give you this. I'm going to give you the practice final, and I'm going to give you something else I'm calling the final exam study guide. I'll have the answer key for this on Thursday. Our final exam is next Tuesday. At this point, whatever you haven't turned in yet, it would be the same if you turn it in on the day of the final as it would if you turn it in today. Are you with me? Now, if you want me to grade something by Thursday, just let me know. I can try to make time to look at it. You with me? Otherwise, you can just hold on to it, because at this point, everything should be geared towards getting ready for the final exam, right? So you have competing interests. If you want your grade to increase, you should look at making any corrections to any tests you haven't corrected yet. So does everybody understand that quiz 1 corrections, for example, if you haven't done them, you can still do them? If you get enough of them right, you can get some points back. You won't get anywhere near the points you could have gotten back, but you can still get something. So for me, if I was a student, I would work on any test corrections I haven't done yet. That's the heaviest weighted thing, the tests. So that's the quickest way to kind of boost your grade, right? Plus, added bonus, everything's on the final. So whatever the shit you do right now is going to help you get ready for the final too, right? You guys with me? I would be also concerned about the most recent homework, obviously, because all the stuff is going to be on the final, right? We didn't have a test on the most recent stuff until the final. It's all going to be on the final. So let me give you this. This is the practice final. All of 9, right? All of 9 is extra credit.
Okay.
Yeah. Bum, bum, bum. Oh, real quick, did anybody, let's see, this is a really old one, yeah. All right. Oh. Here's what I'm calling the final exam study. So I want to focus today on this thing. We might do a little bit off the praxis final, but I want that to mostly be Thursday. All right. So this is well, so I don't know if this will come as a shock, but I'm a major geek. So when I was in college, I would study to the point of knowing if you said chapter 4, I would say this and this and this and this were in chapter 4, right? So I get to that point. You don't have to do that, my God. You just have to know the ideas. So let me show you what I try to do with this, and also why there's space between the ideas. And also to my people at home. Hey, people. People at home. Da-be-dee-da-dee. All right. There we go. So, what I try to do here, it's a really good idea to kind of gather for yourself the main concepts from the semester, and then you can identify what you feel the weakest with, and then you can focus on that. So I've written down a few general things, but then we're going to drill down a little bit. So yeah, we did chapter 2 before chapter 1, because chapter 1 I found out, if I start with chapter 1, people freak out a bit, because chapter 1 is the word problem stuff. So chapter 2, can anyone tell me anything about sets, S-E-T-S, what we talked about in chapter 2? What did we do with like set A, set B? What kind of stuff did we do?
Open and closed sets.
Okay, open and closed sets. So you have like infinite number stuff versus, so like for what would be an example of an open set? So here's a closed set. What's really weird right now is I can't remember if we actually did open and close, but yeah, I guess we did. Open set would be something like this. It's open, it just keeps going. It's not closed, it's not contained, it's not finite. But what are the basic operations we did? If I give you a couple sets, what kind of questions could I ask you?
Like the intersection and the.
All right, intersection
Is union of them?
and the union. What was the symbol for intersection?
I know one was an N, one was a U.
Real quick,
I just
all right.
remember one.
Which one means or? Which one means and?
Or is like the.
Sure, or is this guy. I love this guy because it's like you or you. I don't know, somebody do this shit, right? So I like this is like or. One of you guys, I don't care, just do it. And the symbol is like a letter A that lost the middle bar. Maybe, right? Now it's all a question about, can you remember which is which? Which one of these means the answer has to be those things that are in both? Intersection. It's where the sets intersect. What elements intersect? So this would be and. This would be this symbol. See how it looks like an A that lost the middle bar? Union is or. That would be this symbol, you or you. And the great thing about that is it looks like a freaking U for union. You guys all with me? Okay. So we had that whole discussion. We also had a few more symbols. Can anyone remember any other symbol that were related to sets?
Empty sets.
Empty set, what was that symbol?
The circle with a line through it.
Circle with a line through it.
Element.
Element of, kick ass, what would that look like? Just a little e-dude, right? That's easy to remember for element. Become an e-dude. Become an e-dude there. So that's an element of. And of course you could have not an element of, right? What would this mean? You guys remember?
Is that A and B?
No, A and B would be using this, right? Equivalent, good. So this means equivalent. Does that mean that they're equal? No, it just means that they have same number of elements. You guys kind of with me? A little bit, okay. All right, I like it. I like it. We also had another symbol. By the way, I can't remember if I said this directly, because in the homework I noticed something. This relates to a single element of a set. So I could say like 2 is an element of the whole numbers, right? I would never use this symbol if I'm trying to relate to sets. So if I wanted to say A is a subset of B, A is contained in B, what symbol would that be? Yeah. So this would mean A is a subset of B. It kind of looks like the less than symbol that's been curved. Does that strike a bell? Does that sound familiar? So the way I would use this is if A was 1, 2, and B is 0, 1, 2, 7, A is a subset of B. All day. What if C is 1, 2? Is A a subset of C? Sort of, but I would use this. I would say A like that. What does that mean? Yes, it's sort of like less than or equal to. It's a part or it's the whole thing. So, or I could also, of course, say this.
Would it be a proper subset?
Yeah, good. So this would be a proper subset. So that means it can't be equal to each other. This would mean it's a subset or they're equal to each other. So couldn't I say, is this true?
Yes.
Totally. Is this true?
No.
Hell no. Is this true?
Yes.
So I can say either one of these. So if these are my sets, I could say either one of these. As long as equivalency equals is a part of the possibilities, it's good. Okay. So all this coming back a little bit? Yes?
On the practice final, there's like a B that has a line over it. Can you remind us?
Oh yeah, thank you. It's probably just me, but it is warm in here, correct?
Yeah.
It's freaking 75 in here. Hold on. Oh, I see. Okay. Freaking 75, Jeff. All right. There we go. Oh yeah. All right. So why? Let me ask you this. Okay, real quick. Does anyone remember what this symbol means? Good, not B. Why is that something you can't really answer with what I've given us so far? Oh, there it is. Yeah, sorry. You don't know the universe. Okay, sorry. I thought you meant inverse. You meant universe. I don't know what's possible, right? So not B. If I tell you the universe is 0, 1, 2, 6, 7, what's not B? What's not in B? 6. Good. So you can't really answer this question unless I know what the whole set I'm talking about. What if the whole set was whole numbers? Not B would be everything that's a whole number except 0, 1, 2, 7. There's no quick way to write that. I guess, so what's more important right now is the symbols. What does that mean, right? Does this sound familiar? Okay, good. Okay. Then we move on to problem-solving strategies. Word problems. Does anyone remember any of the strategies. What you got? Draw a picture, kick ass. Somebody else, what's another one? Anybody remember another one? Guess and check, I love it. Anybody else? Solve a simple problem, that's one of my favorite ones. Doesn't always work, but when it does, it kicks ass. I'm not sure if I can remember all of them. Remember one more at least right now. Use a variable, there we go. Oh, I remember another one. I think I heard it. One very nice. Look for a pattern, kick ass. Make a list, right? That's pretty good, yes.
We are gonna be tested on like number systems and different bases, right? That are
Oh,
in chapter
oh yeah,
one.
did I skip that? Yeah, sorry. So number systems, what are the number systems we talked about, for example? Mayans, Babylonians. You look so excited.
Romans.
Friends, Romans, comes from me. Okay. So we're gonna have the numbers. I'm gonna give you exactly the same thing I gave you before. So, do you remember I gave you like the Mayan? Does anyone remember what was weird about the Mayan bases? The Mayan base. What was the Babylonian base? What base did the Babylonians use? We used base 10. What did they use? It's crazy ass people. Not 20. That's more like the Mayans almost. 60. They're the ones we stole the idea of minutes and seconds from. Right? We're like, thanks, Babylonians. Sorry you had to die out, but we'll steal that for us. Mayans aren't quite base 20s. Does anyone remember why? Something weird happened with the Mayans, but they had a very good reason to do it. Yeah, why did they want 360 to show up? Because that's roughly a year. And of course they were, like any ancient civilization, they were mostly concerned with agriculture, which of course we are too, but it doesn't rule everybody's life. Different bases, what do I mean by that?
Like
Base 4, base 16, base whatever, right? So if I go above 10, we have to introduce what? Letters. The book uses T&E, which is dumb. I'm sorry, it just is. Base 16 hexadecimal uses A, B, C, D. So A would be what? 10. So 10, we need 2 digits to represent the idea of 10. If I'm in base 11, I only need one, but I must only use 1 digit for base 10, right? For number 10. You guys, am I with me? So base 10, what's the highest single digit? 9. Base 20, what would the highest single digit be? 19, right? So we just go A, B, C, D, E, F until we get to what we need for 19. Are you guys, am I with? Before you ask it, there exists like base 4,287. There exists base pi. We're not. This is unfortunate. Yes, so there will be other number systems. There will be different bases. One really good, besides the practice final, one really good thing to use to get ready for the final itself are the old practice tests and the old tests themselves, right? Old quizzes. Because I like to kind of ask similar questions. Right? I'm not saying right now that I'm going to use the same questions I've used before, right? There will be some other conceptual questions that aren't directly related to problems I've asked you before, of course. It's all kind of with me, but there will definitely be certain kinds of problems you're going to see again on the phone, obviously. Okay. How are we doing so far? You guys okay? Do you think this is helpful? If it's not helpful, we can stop it to something else. Yeah. I guess. Also, thinking about it. Did I have? No. There you go. Oh, did you get a practice final? No. Onion, did you get stuff? Okay. And yeah. There's no markings on it. I'm assuming it's okay. Also, see me after class real quick. I just wanted to ask something about that. Okay. Where am I? Oh. So chapter 1, problem solving strategies. Then you give me a word problem. Normally I'm going to ask you something like, explain to a student why this would work, or pick the best strategy and then try to apply it, those kind of problems. You've seen that kind of problem from me before. Chapter 3, we got the whole numbers. We talked about addition of whole numbers, subtraction. So for example, I gave a couple examples. There's the takeaway kind of model. There's the comparison approach. Does anyone remember any other subtraction approaches? There's takeaway, there's comparison, measurement model. That's of course using like a number line kind of idea. Of course you also have, if you have the measurement model with the number line, you also have the set model. I like it. But in terms of like takeaway, that kind of thing, what's the other main one? Missing add-in, kick ass. So if I say what's 7 minus 3, a student can think, well, what would I add to 3 to make 7? And why is that a really good approach to start with when you first introduce subtraction, is to have a student think that way? 7 minus 3 is the number that I would add to 3 to make 7. It's what 3 is missing to become 7, right? Why is that a really good approach? They already know addition, exactly. So what do I keep, I think I've said this to you. This might be my most repeated thing to you guys. Whenever you're teaching something new, you make connections to something old, right? So that they have something they feel comfortable with that they can build into this new freaky ass thing, right? I like it. Because again, what's really weird is we're taking these kids and we're putting them through in such and so, in like 10, 12 years, what took civilization centuries to work through. If you think about it like that, that'll trip you up. Do you understand what I'm saying? No? Okay. Here, I'll keep going, Josh. So we got takeaway, comparison, we got missing add-in. And of course, you have the set model for that, all kind of business. The properties, right? This is where we first talked about associative, commutative. What other properties are there? Distributive. Closure, kick-ass. We introduced some later too, so it doesn't really apply for this one, but later we talked about identity. Well, it does apply to this one, zeros identity. Later for multiplication, we've got the multiplicative identity, correct? Eventually we talked about inverses, right? You guys sort of with me? So if I said, what is the additive inverse of 4, what would that be? Additive inverse of 4. What's that? Negative 4. It's basically, what do I do to cancel it out? But when I say additive inverse, all right, what's the additive identity? 0. So inverse always says, whatever the operation is, what gets me back to the identity? So if I start with 4, what do I add to it to get it back to the additive identity? I add negative 4 to it. So basically our idea of additive identity is the opposite side. What is the multiplicative inverse of 4? So what's the multiplicative identity? 1. Trembling finger went up. So what's the multiplicative inverse of 4 is the number I multiply by to get back to the identity. What do I multiply 4 by to make 1? 1/4. Okay. So multiplicative identity is another name for reciprocal. I'm sorry, multiplicative inverse is another name for reciprocal. Oh boy, so whole semester in one day, right? Multiplication definition, what do I mean by that? What's the basic definition for multiplication? Repeated addition, which of course is going to be, again, the first method you use when you teach multiplication because they will understand addition at the point. So 2 times 7 means 7 plus 7 that kicks ass. Real quick, how is 2 times 7 different from 7 times 2? Computationally, they do not differ. Conceptually, what's the difference? 2 times 7 is 2 sevens. And of course, 7 times 2, 7 twos. And just to remind you guys, I know I said this a few times, but that's where parents go a little insane. They're like, what are you doing? They're saying, but again, people don't become born understanding that multiplication is commutative. So you want to build an idea, 2 times 7 is 2 sevens, 7 times 2 is 7 twos, and they go, look, they're the same thing. Does that always happen? I don't know, let's investigate, right? Okay, so there is a reason for that. And of course you got division. Yay! What's the definition for division? It's kind of nice. Repeated subtraction, and that's how we built those algorithms to kind of eventually get to our long division algorithm, right? Okay, this is so exciting. Sorry. Mental math methods, right? What shit are those? Can somebody give me, does anyone remember what this might reference? Maybe I'll start us off. One of my favorites. Compensation. Right, so we have compensation for addition, subtraction, we have compensation for multiplication, division. Anybody remember anything else? Something else starts with the CO. Compatible numbers. What's an example of compatible numbers? Let me show off my, is that an I or an A? My beautiful spelling skills.
Numbers that make 100 or 10.
Yeah, numbers that make a whole number, more than likely. So if you have 14 plus 5 plus 16, you can do 14 plus 16 is 30, right? So you look for those compatible numbers first. Back in the day, when we had to balance a checkbook, does anyone still balance a checkbook? You guys just go to the bank and, you know, back in the day we used to say, you want to balance your checkbook because the bank could lie to you, but I'm not going to take the time, I'm sorry. But when I had a balance checkbook, you do all the pluses and you do all the minuses, and then you, at the end, do that. So those are compatible in a different way. You with me? Positive numbers are compatible because you add. Negative numbers, you add them up and then it gets to be negative, and then that's why at the end you put those together at the end, right? So compatible numbers, actually, the idea goes beyond what we even talked about. I can't even remember another one. What's another? Anybody remember another one?
Left to right addition.
Yeah, then you get into all these. Yeah, that's kind of like a step in the direction of just lining them up. So that's sort of like an intermediate algorithm kind of idea, left to right. Addition. We also had some estimation methods, right? Front end with adjustment. Those are a little crazy. Let me think. Oh, what about for subtraction? There was a specific one. Equal additions. Does anyone remember what equal additions referenced? There was a problem on the test. I think it was something like, what was it, Jeff? You could do it. 145 minus 39, or something like that. And one way to make this easier to do in your head is to add 1 to both. And again, the whole idea is, what is subtraction trying to get at? What physical idea is subtraction trying to get at? Starts with a DI, I agree. It's the distance. So if I add 1 to both numbers, they're still the same distance apart. So the difference I take is going to be the same because it's trying to measure the distance. So equal additions make sense because I add 1 to this, I add 1 to that, they're the same distance apart, except now it's easier to do it, right? Remember? Okay. You guys doing it right? Again, at any point, if you want, if you're like, here, God, just stop. Can we just, let me know. Chapter 5, we got the prime numbers. We got into divisibility rules. Can somebody tell me the rule for 6? How do I tell if something's divisible by 6?
The 3 method and the 2 method.
Say again?
Is it both the 3 method and the 2 method?
So be specific.
Like, if you add all the digits
Good, so it's gotta be even, which is the rule for 2, and it's got, all the digits have to add to be a multiple of 3. If it's both, then obviously it's divisible by 6, right? You guys sort of with me? Now, can anyone figure out, right, why the rule for 8? Is it, I really want you guys with me. Rule for 6 is, if the rule for 2 and the rule of 3 works, it's divisible by 6. Why does the rule for 8 not work the same way? You guys know? So what do I mean by that? Why can't I just say, is it even? What's the rule for 4?
The last 2 digits.
Last 2 digits have to be divisible by 4. So why can't I just go, okay, if it's even and the last 2 digits are divisible by 4, then it's divisible by 8. Why does that not work? You're like, dude, I don't know, man. What the shit?
Because it's not the fully,
What's
but
2 and 3? They are relatively prime. So they don't have any influence on each other. Every number that's divisible by 4 will also be divisible by 2, correct? So if it's divisible by 2 and it's divisible by 4, that doesn't mean it's divisible by 8, because everything that's divisible by 4 is divisible by 2, right? I don't know if you guys are with me. So if the 2 numbers are relatively prime, I could apply both rules to get a rule for their multiplication. Are you guys at all with me? So if I apply the rule for 3 and the rule for 4, well, if it works, the number will be also divisible by, if the rule for 3 works and the rule for 4 works, it will also be divisible by 12. Yeah, because 4 and 3 are relatively prime. Maybe? Okay. GCF and LCM, I think we did a ton of those, right? Of course, you have all the different methods. You have the prime factorization method. You have subtraction, which leads to division, because freaking division is subtraction, right? It's just repeated subtraction, blah, 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 blah. Then everybody's favorite, fractions, right? Region models, LCD, mixed numbers, what they mean, how to add fractions, subtracting fractions, blah, 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 blah. Okay. We proved why dividing is the same thing as multiplying. The reciprocal, all this kind of stuff, right? You guys semi with me? Okay. Then we got the decimals, which of course decimals are just specific fractions, right? If you look at it like that, it's kind of nifty. So for example, 0.7, what is that as a fraction? 7/10. So what's that rule to see if a fraction will be a terminating decimal?
if it's made up of 5 and 2s.
If the bottom is made up of only 5s and 2s. Because then, if it's got less 2s, you give it more 2s, and then it becomes a multiple of 10. If it's got less 5s, you give it more 5s, and then it becomes a multiple of 10. If the bottom is a multiple of 10, that fits in our number system, it becomes a decimal. So all decimals are special fractions. 2/3, is that going to be a terminating decimal? No, I can't make that fit into our base 10 system, because I cannot multiply 3 by a whole number to make it become some multiple of 10. I can't. You guys understand? Is that cool? Okay. Place names, of course, tens, hundreds, thousands, blah, 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 blah. Ratios, percentages, of course, ratios lead to proportions, right? So this is the more recent stuff. I like it. Now, obviously, real quick, the word percentage, for example, this whole sheet, there's a lot of shit to do with it, right? There's the is over of business, there's, how to convert a percentage to a fraction decimal, there's how to do what is 28% of 38, blah, 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 all those kind of things, right? So there's a lot that's wrapped up into each one of these. This is just, to me, like a surface level, okay, what do I feel the least connected to? What do I feel the least comfortable about, right? And then you can go drill down. And then, of course, the most recent stuff, integers, we finally admitted there's negative numbers. We're better than we used to be in the past as humans. We understand that negative numbers mean something. And my joke, of course, is always the bank really understands there's negative numbers. Set models for those, including like the black and the red chips. which is a really useful thing. Money is good for older students. The younger you are, the less you're going to understand money, so the less useful that example is. But then we talked about a few other ones, like digging is negative, is subtracting, or negative, climbing up out of the hole is positive. That's a really good one. And again, you're always thinking about something I do a really bad job of, and I'll be very frank about this, is, especially in this class, you could come up with ways to do negative and positive, so they're physical interpretations that the students could do in class, not just with chips, but where they're walking around. So you could talk about negative and positive being, positive is walking one way and negative is walking the other way, right? So you could have like a big number line on the ground, not as fun as like a big piano, like in the movie Big, but still, so you stand at 0, and positive means you go in the positive, negative number would be you go in the negative direction. So something physical they could do, instead of just manipulatives, because even that on some level is, you gotta bring the chips, you gotta have chips. And what if you didn't have any of that shit? Can you just do something physical wherever you are? Okay. Oh, okay. I think I got it. Okay. All right, so there's obviously a ton of stuff in each little subsection of this, but this is a good surface level thing. So let's look at the practice final. Obviously, the actual final is not going to quite be this long. This is a decently long dude, right? The last few, this was an extra credit section, so if I do put some of this, I think all of you should be able to answer these questions, but again, it's not really, yeah.
C is undefined, right?
I love it. So I meant to talk about this earlier. So like, why is the square root of negative 16? What do you guys think that is? Could it be 4? No, because 2 4s don't multiply 16. Could it be negative 4?
No.
What's negative 4 times negative 4?
16.
Yeah, so this officially is not real. And besides Ryan, does anyone else know what the actual answer is? So you guys remember, I showed you that one video, didn't I, where the guy picked the thing up and it was all colorful? Do you guys remember that? Didn't I show you that one video? Like, maybe. Okay. So this would actually be what's called an imaginary number. It should be called lateral numbers, but that's okay. So this would be like 4i. But that's beyond the scope of us, right? I wish we would teach this earlier, because otherwise, when you do get taught this, you feel like, and then of course the name imaginary, you're like, okay, now you're just being really blatant about the fact that you're just making this shit up. But no, these exist. They have reasons, they have purpose. But don't worry, that's outside of the realm of us. So if I gave you this problem, you would just say not real. Or if you said 4i, a little cheer, right? Okay. All I is the square root of negative 1. We just call it I. Just because that's weird to look at, so we replace it with a letter. Yeah.
So on the test, you would take not real as an answer?
Totally.
Okay.
Yeah. And again, you, like the square root of 81. What's the square root of 81? 9, 11. But again, this section is officially extra credit, so if I put it on the test, it would be a bonus question. Because officially I didn't make you do homework for this, so I'm not going to do that. Even though you all should be able to do all of these. Okay. Except for this one. What's weird about this one?
It's a fraction as a.
Yeah, so let me ask you this. What's the square root really do to 9? Let me say something weird. It cuts 9 in half multiplicatively. If I cut 9 in half additively, I get 4.5. 4.5, yes? If I cut 9 in half multiplicatively, I get 3 times 3. So a square root cuts a number in a fractional part multiplicatively. What is exponents? What are they based on? What operation? Multiplication. So what's another way to write the square root of 9 is 9 to the 1/2 power. They both mean the same thing. So when I teach my students this, I actually tell them this: I wish we had never invented radical notation. It's one of the least useful things that's ever existed. These mean the same thing and they make more sense. For you guys, it might not make much sense at all, because if you've learned about, anybody feel like they never learned about fractional exponents? Or some of you guys are like, maybe I forgot about it. Okay. Normally you learn about them in like intermediate algebra, but again, it depends on your teacher if they threw that out for some reason. Okay, all right. So again, this whole piece down here, if it's gonna show up, it would be bonus. Okay, I like it. So, take a glance through the practice funnel and tell me if anything kind of jumps out at you as immediately concerning or something you completely forgot about. Or just looks weird. Yeah.
Number 5.
Oh. This one?
Yeah.
So let's see. Did you look it up? Yeah, I can't remember what past Jeff wanted. Oh, good. Okay. Oh, yeah, of course. I didn't feel like, making all these symbols, so I just referenced this. Is that cool? Yeah, so that's what this is referring to, is this problem here. And if you want to, you can go back to the test we took on this. So like I said, I'm going to give you all the same stuff. So what did I give you? I believe I gave you the Roman numerals and what they meant. I gave you the Mayan basic. I think those are the only two things I gave you. No, I also gave you Egyptian numerals, correct? Okay. Everything else I had to memorize. So what was the Babylonian? What did they use for the numerals? Sticks and triangles, exactly. Like sticks and Pacman, right? Or less than symbols, if you wanted to do it like that. There was also another symbol, but it was just basically a stick with another stick on top. Do you guys remember where that was? Subtraction, yeah. I think you're thinking about Roman. If you put a line over the top, it multiplies. But what's that? If I have a symbol for 1 in Roman and I put a line on the top, what does that actually mean? You guys remember?
Oh, isn't that like I remember I got it wrong on the test. It was like 4,000.
Yeah, so if I have a 4, a symbol for 4, and I put a line over it, that's 4,000. So a line just means multiply by 1,000. But what is the actual symbol for 1,000? Do you guys remember? Anybody remember? Roman symbol for 1,000? Yeah, whatever, Jeff. You and your puns. M, right? So you wouldn't write one with a symbol, you would just do an M. So what does it really kick in? What's the one thing about Roman symbols? How would you write 4,000? Would it be would it be M? What's wrong with that? What's wrong with M? You can't have more than 3 of the same symbol immediately in a row, right? So how would you write 4,000? The symbol 4 with the line over it. That would be 4,000. Is everybody with me? So if you ever catch yourself doing a Roman numeral problem and you have the same symbol 4 times in a row, you're wrong. You got to change it. And again, some of the rules, I agree, are silly, but some of them actually maintain the integrity of the system. We weren't around when the Romans made this up, so we couldn't help them make it better. Okay. Is that cool, Ryan? Was your question really more like, what the shit problem is this referring to?
Yeah, I didn't know that, like, you were referencing to the...
No, I'm glad you asked, because it's good. I want to make everybody understand what I meant, and I was just being lazy. I didn't feel like making the symbols and put them on there. I'm like, just go to the book.
So does that mean you're gonna put the,
On the test, I will actually not be lazy. I'll actually make the symbols,
okay.
right? On this, I was just like, just go there. I just needed a problem for you to try. Yeah.
Number 8, I remember having trouble explaining why that works.
Oh, here?
Yeah.
Okay, all right, so one thing to really remember that helps with proof problems, what does that symbol mean, by the way?
Is divisible by.
Come on, yeah, 7, well, be careful, not is divisible by, divides. So for example, I could write 3 divides 18. That means 3 goes into 18 evenly, correct? Why does 3 divide 18? Because 3 times, holy shit, is 18, okay. So, if I see this, if they tell me this is true, what can I immediately write? A equals, if 3 divides a number, that means that number equals 3 times something, correct? So 7 divides A. So the A is 7 times something. I don't care what symbol you use, right? Normally we use letters. You can use a little happy face, frowny face, however you're feeling, right? This could be the mood ring kind of problem. So that's a huge thing to realize. That's very often very useful in proof problems. So we know it's even. What does that also mean? If A is an even number, what other divisibility rule could I write? Or what other thing could I write? If A is even, what divides A? 2 divides A, which means that A is 2 times n. So 7 is a factor of A, and 2 is a factor of A. Are you with me? Are 7 and 2 relatively prime? Yes. So I really want this to make sense. If 6 is a factor of a number, and 2 is a factor of that same number, is 12 a factor of that number? Why not? Why not necessarily?
They're not relatively prime.
Not relatively prime. 2 is a factor of 6. So, for example, is 6 a factor of, you could do it, Jeff. Yeah, sure. Is 6 a factor of 18? Totally. Right? Is 18 even?
Yes.
Yes. So is 12 a factor of 18?
No.
No, of course not. 6 has 2 in it. If 6 goes in, it's already understood that 2 goes in, right? Okay, so one way to explain this is that, well, you could say, since these are relatively prime, then it has to be 14. That would be awesome. That is the super technical way to explain this. You could also say that whatever A is, when you prime factor it, it's going to have a factor of 2, and it's going to have a factor of 7. So it's got to have a factor of 14. You can just recombine those factors. Does that make sense? It's another way to do it that's less technical. Yeah.
So the idea of relatively prime is if you, as long as you have one prime number within.
No. So here's the idea. Is 8 prime? Helen, are 8 and 5 relatively prime? Yes. And just to make sure you understand, 8's not prime, correct? Is 9 prime? You agree with me? 8's not prime, 9's not prime. Are 8 and 9 relatively prime? Yes, because what does relatively prime mean? They share no factors between each other. So that confuses students because neither one are prime, correct? So why do we call it relatively prime? Because the idea of prime is it can only be factored a certain way. So relatively prime means they don't share any factors besides 1. But prime means you can only break it down as 1 times itself. So there is kind of like the idea of prime between the two, even though neither one has to be prime. So, if a number was divisible by 8, and it was divisible by 9, what else has to be true? It has to be divisible by 8 times 9, 72. Okay, fine. That's basically all this is saying. Same idea. Is that all right? I will agree with you. Those are supposed to be the hardest problems. Fully explain. By the way, have you guys picked up on when I ask you a question like, here, 7, or what is it, 13, 12, 11, 12, there it is, 12, okay. When I ask you a question like number 12, some of you guys don't quite fully get everything out, so the main thing is you're talking to a student. I need you to go through like, okay, you've made this mistake. Here's why it was a mistake, and here's the correct way to do it. So a few of you guys just kind of do the problem. And I'm like, I'm pretty sure you wouldn't just, a student would come to you and go, well, you do this, go away. You know, I'm pretty sure you wouldn't do that. That's the worst thing in the world you can do. So I kind of like that problem. Do you see why a student, and this is an actual thing that has been said before. Right? Okay. So I'll let you think about that. Okay. So let me do this. I'm going to show you some videos from chapter 8, because we haven't watched videos in a while. So I want you guys to see these kids doing stuff. And then we'll, does this sound, we can do this. We can keep doing some problems from the practice final, or we can break for the day, and then Thursday will be review day. You'll have time to try some problems for the practice final between now and then. Either way, I'm open to. So let's look at these videos, and then I'll see what you guys feel like doing. Oh shit, now let's see if Jeff remembers his. Holy crap. No, go ahead. Alright. Bless you. So see, today we got people from grade 2 starting us off, and then mostly grade 5 and 6. So let's take a look here. Oh, I gotta turn my camera on. Oh shit, probably should also show you the video.